a very nice introduction. Swiss-German, certainly not. It's a pleasure to be here for sure, and an honor to be selected as the Alumnus of the Year, and I certainly appreciate that. It was great fun arriving back yesterday, because we don't come back to the prairies very often, and you know I'm a prairie boy. I'm from a tiny town outside Medicine Hat. And my wife and I drove down and just thought how beautiful it was on the wonderful flat prairies without any trees. And coming from, well, where we've been living in Switzerland, where there's lots of hills and lots of trees, and it's very strange to come back here. And it's very crowded, I might add. And of course, it's a very densely populated area. And I'm thinking about the fact that the people in Switzerland ask me about where I come from, and I say, well, I come from a little prairie town where there's no trees or anything. And I say, oh, you must really like it here, and all these mountains and everything. And I just say, well, it's nice, but it kind of blocks the view. So it depends on how you look at it, you know. I wanted to say something about the overall topic of nuclear waste and how it should be dealt with ultimately, and why I think so. And it's based on a lot of years of research, work that's been done in Canada, in Switzerland. I've worked as well with Swedish and Finnish programs, and even occasionally with the unfortunately stopped American program, which is politically goes nowhere. But it's worthwhile keeping in touch with them all because of learning about the technology. And I've tried today to go through some aspects of the nuclear waste issue about why I think this is the right way to deal with it. It's not a highly technical talk, but I'm quite happy to take technical questions, and I have some technical slides, so if you have really sort of scientific points, I'm happy to take them. This is a sort of a more general overview of the nature of the problem and what I think is the solution. I just make a comment first. As you know, especially nuclear power is the whole issue of nuclear power is enormously controversial because of various incidents, accidents that have occurred. Make a couple of remarks about that, and then I'll go into why I think nuclear waste disposal is necessary, and then I'll touch on some frequently asked questions, because you would be amazed at how often we get these simple questions that are, you know, framed like, why don't you do this with the waste? That sort of question, and I think it's worthwhile answering those questions right up front. I can then talk about how geological disposal can provide safety, and what are the sort of ground rules, the boundary conditions for achieving that, and then say something about, well, I hope, about how long it will take for it to happen. It's a slow process. You surely know that there are, you know, sharply divided views about nuclear power in general. It's interesting to look at some of them and where they come from. I just looking at some famous people recently in their statements, even since Fukushima, and you see people like Hansen, who you might know as the climate modeler, saying things like next generation safe nuclear power is an option we need to develop. And Lovelock, who's the author of the Gaia theory, you know, the Earth is an organism that adjusts, or whatever, looking at it and saying, okay, renewables are a good thing, but, you know, the only thing really that's going to contribute that doesn't cause global warming at all is nuclear energy. The former head of the EPA saying, you know, there's nothing really else really like this in terms of affordability and lack of emissions. And Jeffrey Sachs, who's the director of the Earth Institute, saying, well, you need to take a mix of everything, and it's one of the important things in the mix. And then you have the other side, And there are some really strident views, and you probably all have seen those, and they're spoken by other people besides these, but these are just examples. The Green Party's position and Greenpeace and others are saying, no, 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 we want nothing to do with it. These are all, very strongly held views. And I must say, in terms of the nuclear industry, there are also some people who are stridently pro-nuclear. I mean, they would build reactors down the street from themselves and anybody else without thinking about it. And so I think there are some immoderate views from all perspectives. But in some respects, from the point of view of waste management, I say, well, what are you going to do? Whether you hold those views or not, we have almost 450,000 tons of spent fuel in storage now, already discharged from reactors. There's just no point in ranting about nuclear power and saying we need to shut it down and that will solve the problem, because it doesn't deal with the issue of the nuclear waste. And so this is what we face, and this is the material we have to deal with, and you probably know basically what this is. You have uranium oxide fuel pellets that go in tubular fuel assemblies and go in reactors for a few years, and they go into wet storage, deep pools under many, many meters of water, which is what you see in the middle, for usually 10 years. And then they can go into dry storage casks of the type you see here, which are actually from the storage hall in Wirrenlingen in Switzerland. And those are dry storage. The only thing inside the cask besides the spent fuel is helium. Keep it inert. And as you can see, you can work around the cask because they're fully shielded. So you can store the fuel like that for a very long time. Nothing much is happening. It's solid state processes at irrelevantly low rates. But it's storage. It's not dealing with the problem. I'll make a remark here about Switzerland, because I'm going to show another slide in a moment in terms of people's views about nuclear waste and nuclear power in Switzerland. And this is this present situation in Switzerland. We have 5 nuclear power stations, and they produce almost 40% of the electricity. The other 60%, by the way, is all hydro. There's 1% thermal, basically, almost no renewables. Pretty remarkable from the point of view of no CO2 generation for the system. But recently, almost immediately after the Fukushima accident, the Bundesrat, the Federal Council, almost instantly took a decision to get rid of nuclear power. Just a kind of a knee-jerk reaction. But they weren't quite sure how to do it, so they said, but the plants can run as long as they're safe. Well, running nuclear plants, if you keep them in shape, they can run for up to 60 years. So we could be running these plants for another 20 years anyway, despite this decision. So they've made a decision, but they haven't quite made a decision. So we're in a very strange situation. I thought I should mention some things about people's perspectives about nuclear waste, because it's something where, mostly public attitudes are, it might be something like Homer Simpson or something like that. I don't know. But the attitudes are certainly out of balance with the facts, at least to some degree. You can see that 95% of people say, well, there should be a solution for this, but 82% believe that there's no way to do it. It's funny, in a way, you think about it. Think of how optimistic people are about technology in many other ways, and think that they have no optimism here that technology can do anything. It's a curious sort of dichotomy. 50% approve of the idea of deep geological disposal. 63% don't feel informed, and then you can see some examples of that. I think a classic example, surely you will know if you're a chemist, you will know this, that the idea that radioactive waste is produced in similar quantities to other waste as chemical waste is a pretty strange notion, because in the US alone, there's 40 million tons of chemical waste, chemical hazardous waste produced every year, and high-level waste worldwide, it's 10,000 tons a year. So there's a really big disconnect in the perspectives about it, and of course all of that affects the way in which we can pursue managing it because we're dealing with a much smaller quantity, so it's much more manageable in many ways. A lot of people think geological disposal already takes place. It may be because they've heard that there is some waste disposed of, but this is normally low and intermediate level waste, which is not very active material. It includes waste from medicine and industry and that sort of thing, and that goes on all the time. But no high level waste is disposed of. People think that it's sent to other countries for disposal. Actually, the laws in almost every nation forbid that and insist that the waste be dealt with nationally and that it can't be shipped out of the country. And it's dumped at sea. Actually, there are a couple of famous videos of people dumping concrete barrels into the sea from the late 70s, which probably led to this. But the sea dumping was banned, I think, in the 80s. And it wasn't a very good idea anyway, obviously, but this gave some people the view that that was how it was being dealt with. Now, I'm going to now give kind of a walkthrough about why I think it's necessary. And really, what's behind it is, it's pretty apparent if you've done any risk analysis and if you think about it, and if somebody is familiar with risk assessment, you'll know. We're dealing with comparative risk assessment. I mean, the purpose of risk assessment is to inform yourself so that you can make decisions that are evidence-based. I know politicians might not like to hear that because they don't do much that's evidence-based as far as I can see, but anyway, but our job is to try to make sure that we quantify this and we have a proper basis for making decisions. So the first thing you have to look at is, well, what are the properties of the waste you're dealing with? And this is spent fuel, and this is the radiotoxicity of a ton of spent fuel. The toxicity versus time, now it's a log-log plot, and so I think you're probably all familiar with log-log plots, and so you're not too confused by them. But it can be difficult for some people to appreciate what they're seeing. The radiotoxicity index is just an effective sort of indicator of toxicity. It's not a very helpful thing. It's simply a unit that can make comparison. It doesn't mean very much, but it's convenient for making the display you see here. And basically, you would see the same kind of curves you see if you just looked at radioactivity of all of these individual radionuclides. And so you see that, you know, the toxicity just declines kind of quickly in the first sort of couple hundred years, and then there's a very gradual decline until it's after, say, 100,000 years, it's back to being similar to uranium in equilibrium with its daughter products, that is, with its decay products. Uranium decays to thorium, et cetera, down the decay chain. That's what you see over here. You see the daughter products, and it goes into the range of the equilibrium in 100,000 years. So we say, roughly speaking, well, what's our target for containment, for isolation? Let's say of the order of 100,000 years. It might be something like that. Of course, the radioactivity never really goes away because you have isotopes like uranium that have half-lives of billions of years. So, but of course, the virtue of that is their radioactivity is very low, so they're not all that hazardous. It isn't helpful to do linear plots, obviously, but some people have difficulty with log-log plots, and I just say, well, but there's no point doing a linear plot because you can't see anything. So it's just to illustrate how futile the whole thing is. If you're trying to put these in perspectives that people are perhaps used to. One obvious issue then, you'd say, well, you've got all these radionuclides in there. Why can't you do something with them? You know, why can't you reuse them or recycle them in some fashion? And there are different schemes. On the top, that's a light water reactor fuel cycle. So you mine the uranium, you then enrich it from about roughly 1% uranium-235, the fissile isotope, up to, say, 4%. And then you irradiate it, you fabricate it and you irradiate it in a light water reactor, goes in storage, goes to waste disposal. That's a once-through fuel cycle. And another once-through fuel cycle is in the bottom. That's the Canadian one. Okay, Canadian reactors operate on natural uranium, so they don't have to enrich. And heavy water is a better moderator, so you can operate a reactor with natural uranium oxide. But the same process you have, you irradiate it, you get the power, and then the fuel goes into storage, and then it can go to disposal after it's cooled. Now, a big issue has always been, can you really recycle and transmute and all that sort of thing? And yes, but there's an awful lot of these optimistic spreadsheets around, I have to say. I get somewhat frustrated with physicists walking up to a blackboard, writing neutrons in, spallation products and transmutation products out, therefore it can be done, and walking away. Meanwhile, all the chemists and chemical engineers have to build the damn reprocessing plants and deal with all the decontamination factors. And I'm not all that optimistic, because I've seen what those are, and I've seen the costs of them and the complications. But the scheme is something like this. After you've irradiated the fuel and you put it in storage for a while, then you can reprocess it. That's an aqueous reprocessing step: dissolution in nitric acid, extraction of plutonium, separation of fission products. You extract also the other transuranics, so you can burn the other transuranics in a fast reactor and get rid of them, because they have these long half-lives, and you might want to get rid of them, so that you can put them through the fast reactor, and you can actually produce more plutonium too, that you can put back into the fuel, and you can go in a cycle, and you can really be a lot more efficient. You can use much more of the uranium. You can burn away some of the actinides, but there's been an awful lot of optimism about this, and we've struggled with this over the years with the people who have to deal with waste disposal. Realize that after it's all finished, we still have all sorts of waste to deal with. These people have just written it on a blackboard. They haven't solved the problem. And we're really not solving the problem by doing this. I'm not saying it's impossible. I mean, technology can always come up with something, but any of you who's done chemistry knows that, efficiency of separations and chemical separations and all that sort of thing has to be pretty impressive. And in this case, it has to be better than 99%, or it's not worthwhile. It's problematic, and I think the other problem is that it's exceptionally expensive. Spent fuel reprocessing plants are in the sort of over 10 billion range, as are the transuranic fuel fabrication plants. The only ones that have been operated, by the way, are not working very efficiently, and one of them was shut down altogether, the one in the UK, the MOX fuel fabrication plant. Fast neutron reactors, well, there are a couple in the world. They're in Russia. They're very expensive too. So there are some real challenges about them. I'd say that even if it works, we've seen the spreadsheets that indicate the flows of the wastes that come out. We know that the wastes that come out are comparable to what we have to deal with spent fuel anyway. So it doesn't solve the problem. It'll extract more energy, but it doesn't solve the waste problem. So we've had Greens, in particular Greenpeace, saying, well, we should just guard this stuff forever, believe it or not. It's an extraordinary thing when you think about it. They've suggested, controlled massive concrete constructions at the surface. Well, it would be like our facility here, except we would have to rebuild it every, 100 years, I suppose. Replace all the casks and something every 100 years. But for what time frame? I mean, I showed you the decay curve. For what time frame are we talking? Tens of thousands of years anyway. Clearly I don't need to give anybody a history lesson about which is more stable, societies or geology. Okay? It's pretty clear what the situation is. The question is finding the right geology. People frequently say, well, why didn't you dispose it in space? We should just extract the really bad stuff and shoot it into the sun. But, despite all of the improvements, it's still true that 5% of rocket launches fail. Still. You can see it from the number of satellite losses, for example. And so you can see that this is an absurd idea, but actually it's suggested to us. And, so we've got then deep geological disposal as what's left, really. It's, find a very, very stable location that's suited to disposing of the wastes and proceed with that. It's got a long history. The U.S. National Academy of Sciences proposed it in 1956, said, well, look, this stuff lasts tens of thousands of years. You're not going to deal with it any other way. Find a way to do it. And of course, it's based on the idea we've got, very, very stable systems that many of them have been stable for hundreds of millions of years. If we can then locate ones that are suitable, characterize them, then perhaps these are the right places for the waste. And geologists are normally they're looking back over millions and billions of years. Now we have to look forward a bit, but we're talking about looking forward 100,000 years or 1,000,000 years or something like that, based on a history of hundreds of millions of years. So it's a challenge, but for stable rock formations, it's not as big a challenge as you might think. First, another thing here, I want to sort of make clear that there is no relationship between landfills and deep geological disposal. People frequently raise it with us and say, oh, well, we just want to build a landfill like the one over there that leaks, like Love Canal, or, that kind of thing. And, well, clearly, the landfills, including hazardous waste sites with, clay trenches and things like that, are frequently built within 5 or 10 meters of the surface. We're talking about 500 meters, far below the active aquifers that connect with the surface, and clearly the water fluxes and everything are totally different. So the potential to remain undisturbed is much greater. And in fact, we even need to consider issues like glaciation. Nobody knows when the next glaciation is, but there have been so many glaciations over the past millions of years that 15 or something like that. I guess that the chances are that there'll be another one within 100,000 years, within the time frame of the repository, which means you have to have it at a depth that it can't be removed from the surface. So clearly what we're after is something like this, a kind of a multiple barrier system with the waste in long-lived disposal canisters surrounded by, we use bentonite backfill. All you Lethbridge people know all about bentonite, don't you? Because you have this muck in the valley here. It's wonderful stuff. And a great thing about it is that it expands when water is taken up. And if you have it in a confined volume and it's unable to expand, it instead develops a very high swelling pressure. We place it at high density, and it develops a swelling pressure of about 50 bars. So that swelling pressure closes the pores and makes it much, much less conductive. And of course, it's far below the water table, so it'll never dry out. So it's actually a very effective impermeable barrier. And we put the whole thing into a rock. The idea is to put it into a properly chosen rock at, say, 500 or 600 meters, something like that. So what you really have to do is find a very stable situation from a geological point of view, an undisturbed setting. You can't have raw materials lower. Can't have gas at a level below the repository horizon, or people will drill through it. So you have to have it in a right place where it doesn't have those kinds of resources. You have to have a very low permeability rock, preferably one that actually self-seals if it cracks, and there are such rocks. So that's the one we've been looking at. And radionuclide retention is important, absorption processes basically. And clays are very good from that point of view. So they have strong absorption for many, many metal ions. So they have strong retention in hydraulic transport. And we designed containers that we hope could last 10,000 years or more. There are probably good reasons to say that, and I'll mention that in a moment. And the geochemical environment has to be good. In principle, there are some deep rocks you could choose that would be very impermeable, like salt formations, but unfortunately if water's in a salt formation, the salt concentration in the water is 12 moles per liter, which isn't very good for any metals or waste. So there are situations that you don't want, obviously, so low salinity waters are better. A key thing is in choosing the rock to choose the right place. Clearly, seismic activity is a strong indicator. Looking, for example, instead of anywhere near these red areas where there's great seismic activity, looking instead into, for example, sedimentary basins or shield rocks, for example, that have been stable for incredibly long periods of time, in which there's no seismic activity, which was years ago when we were studying this in Canada. We were studying the Canadian Shield, and of course the Canadian Shield has, except for the Ottawa area, no seismic activity to speak of. I mean, there's tiny amounts, but the amounts, the earthquakes are very relatively low magnitude and not important. The most important thing there is that there aren't sort of shear zone major fracture displacements in earthquakes. We are often asked about this. Oh yes, but if you put a repository in the ground, what's going to happen to it if there's an earthquake? And people are, convinced somehow that earthquakes are really bad things for things that are underground. And actually, it's where you'd like to be. But the repositories would be located away from major fracture zones. And that's straightforward because major fracture zones are easy to identify, major faults. And that's where the shear takes place in earthquakes, in major earthquakes. And so you don't build there, and that's easy to locate those. As an example, you might remember the great earthquake in Tangshan back in the days when China didn't allow much news out. And there was a great earthquake in '76. It was an extraordinary because it was a huge surface rupture on an active fault, and it destroyed 93% of the buildings and killed 500,000 people. It was hardly in the press here because China was just, they kept all the information in those days, but it was a massive earthquake. And an extraordinary thing about this earthquake is that there were 30,000 miners, coal miners, underground in the Tangshan area at the time of the earthquake, and they all survived. But, 500,000 people on the surface died. And as I said, that's where you want to be, underground, because you can see the intensity of the magnitude decreasing as you go down, the iso intensity lines there. And so some of these coal miners were briefly trapped because the surface facilities, the lift and the shaft, et cetera, were damaged, but they were actually able to get them all out. The underground structures themselves are just fine. And of course, once you backfill them, there's no effect on them at all. So once you put the waste in, it really has no impact. So people often have a very distorted perspective about the problem of seismic activity and its meaning to a repository. Basically, it doesn't really have much meaning. We just make sure we don't build on faults. I'll walk you through now what I call a simplified argument for disposal, based on the approach we have. We have this toxicity versus time curve. I show it again just to point out that the regulator has something to say about this, the nuclear regulator. They say, well, you must assess this for a long period of time, and they say 1,000,000 years. Okay, so we have to do a radiological risk assessment for 1,000,000 years, which is challenging. In Canada, it doesn't even give a timing. It just says, to the time of maximum potential impact on the people who might, ingest some radioactive material. So it's a pretty open question, assessing the risk. First thing you have to do, package the waste. Now, you can put it in canisters made of copper, which can have very, very long lifetimes. Copper is quasi-noble under deep groundwater conditions because, of course, there's no oxygen in deep groundwater, so there's just basically no reaction. It's sensitive to sulfide, so you have to ensure that sulfide somehow is managed. You can't have a sulfide rich environment or an environment in which sulfide will be dominant. But it's one way to manage long-term containment. Surprisingly, carbon steel is actually very good. You wouldn't think so because iron plus water gives hydrogen under anoxic conditions. And so that there's it's an unstable metal. However, the kinetics are very slow. And people have looked at this in the lab, and we've studied it for many years in the lab, and we measure the corrosion rate of carbon steel and compacted bentonite, and we say, oh, well, it looks like the corrosion rate is in the range of 0.001 millimeters per year, something like that. But we can only measure it for 10 years, no more. I mean, it's not realistic that we can make long-term measurements. So a colleague in Japan, Yoshikawa, did a study on a whole bunch of axe heads taken from Yamato ancient tomb. Now this is like 1,500 years old, and measured the corrosion rate of all these axe heads. And interestingly enough, it's less than 0.001 millimeters a year. Now that's 1 millimeter in 1,000 years. It's a pretty remarkably low corrosion. So reason to believe that we could have a good quality canister. So you can take a canister lifetime like this, and you could have 10,000 years in principle, where the red arrow is, something in that range. So we need to get further down in terms of toxicity. And then the question is, well, what happens to the waste itself? The waste itself is uranium oxide, which also, fortunately, is under reducing conditions, anoxic conditions, is actually thermodynamically stable. Because uranium has 2 oxidation states, +4 and +6, that are relevant to geochemistry. And under anoxic conditions, it exists in uranium-4 oxide, the same as we have it in the fuel in the reactor. And in fact, this deposit is something like, averages 10% uranium. It's the richest uranium deposit in the world. And it's been stable for 1 billion years, and it's got very low uranium concentrations, even in groundwaters close to the ore. So our expectation is that the fuel itself is relatively stable geochemically, like with a solubility of something of the order of 10 to the minus 9 moles per liter, something like that. This is the solubility of uranium-4, which is a pretty effective barrier. We use a clay rock. We've been looking at a clay rock for geological disposal. One of the main reasons is, well, it's great impermeability, of course, but it's also self-sealing. If you fracture the rock and expose it to more water, it seals up because it's got partly swelling clays, smectites, as bentonite has. Bentonite is almost entirely smectite, but these natural clay rocks are about 5 or 10% smectite. Highly impermeable, so you only have diffusion-controlled transport, which is really a valuable thing, and I'll show you the evidence for that in a moment. You have to find the rock first, though, and the location. So we have several locations that are possible, and we're looking at those right now, trying to go through an application to the government about the suitable location. And it's this gray layer that you see there called opalinous clay. This is done from a 3D seismic profile. You probably know about 3D seismic, so you take a lot of charges across the surface. It's done in X, Y coordinates, many charges. Then you take all the reflections, and then you process it all. And in a way, it's a bit like a MRI or a CAT scan or something in terms of what you end up with in a high level of detail. And it's then calibrated with single borehole, which goes down and measures everything related to the layers and the properties, and it turns out to be very good, and it turns out to be really effective. So we end up with a real profile of the rock, and we know how thick it is and what its properties are, and in principle, we know what the barrier functions are, and we say, well, if we put a repository in the middle of that rock, you'd get basically substantially complete containment for a very long time. There are aquifers well above and well below, non-potable aquifers, but these might interact at some time in the future. So we looked at this. We are able to detect faults in the clay through the 3D seismics. This is an example of one. So that means we can avoid them. In the location of the repository, we find regions that are unfaulted, and we can find enough rock that is unfaulted. You could locate the repository. So that works. Then we've got the issue of is it really diffusion controlled in this rock? Fortunately, these isotopic methods are really valuable for this. I don't know if you have any familiarity with this, but there are isotopic techniques looking at for example, the shift in the amount of deuterium or an oxygen, 16 oxygen 18. And these isotopes are very valuable because they are indicative of certain sort of environments being separated from other environments. They're not direct indicators of age or anything like that, because these are non-radioactive isotopes. This comes purely from the fact that, you know, hydrogen is lighter than deuterium, so it evaporates more quickly, for example, in ocean water. Okay, and in deep waters, then there's different evaporation rates, so you can get hydraulically isolated regimes showing up with a distinct profile, and we end up with a distinct hydrogen deuterium content here within the clay rock that's impermeable, and in the aquifers a very different signal. This tells us something about what's going on, and in fact the curve is a fit of a diffusion profile. So it shows, in fact, that the rock is diffusion controlled. Our isotope chemists at University of Bern have 9 of these profiles through the rock, different clay rocks, and they're all diffusion controlled. So it's a very good indication that we can model waste isolation in mathematical models from diffusion controlled approach. So I stick some simple math in, and I wasn't sure who I'd be speaking to, whether or not I could stick in the whole equation or not, but the whole equation it's one of those ugly diffusion equations with error functions and things like that. So we'll just forget about that. But we take the simplified version of it, which is actually, you know, quite accurate, and we say, well, we model release here. We have a constant concentration condition of some radionuclide here, and we calculate its transport across. And the time to a diffusive breakthrough to 0.005% of a steady state value is given by a very, very simple equation you see there, 0.03 times the length squared divided by the diffusion coefficient. Now we have all the diffusion coefficients for all the species. We've measured these. So you end up with so I put a concentration graph on here, if you like, from 0 to 100 for the far side of where the aquifer region would be. And so like something like this, if you have a very fast diffusing small radionuclide, the very first beginning of breakthrough is something like 15,000 years. If you have a strongly retained chemical retention, strong chemical retention nuclide, you have an isotope of, you know, plutonium or some metal that is really slowed down, strong absorption, well, it takes so long to break through that it will decay away before it can possibly break through. So most of the radionuclides decay away. There are a few things that don't, but they get through in very, very small quantities. And so the key thing is what quantities. We can calculate those. Based on something like what I just showed, you can see the calculated dose. If somebody drinks the water from the aquifer, the aquifer that's potable up above, and you can see that the radiation dose here is something like 3 orders of magnitude below the regulatory guideline, or 4 orders of magnitude below the natural radiation exposures that people get from radon, potassium-40 in their body, etc. And in fact, you can see the diffusive transport curves that I was talking about there before. The fastest nuclides, the front coming out here, the strongly absorbed nuclides out here in millions of years. But they've essentially decayed to such a low level that these are considered sort of meaninglessly low radioactivity values. You can calculate any number, but they don't mean anything because they're so far below the actual typical radiation exposures. For example, the red line that I show, the potassium-40, potassium-40 is a primordial isotope that we all have in the body, our bodies, and it gives a certain radiation dose because there's a constant level of potassium maintained in the body, has to be. And you can see that the radiation doses from disposal are far, far below that, and are even below the, what you get from drinking a mineral water every day that comes from deep in the ground, which has tiny traces of, uranium or whatever it happens to have in it that are radionuclides, and that's typical enough for mineral waters. So we can see that we can make a good argument that the consequences are very, very low relative to natural radiation exposures. You can put it all, again, you can return to linear scales if it makes you more comfortable. Doesn't me, but anyway, some people can't make sense out of log scales, but most of you are scientists, so I don't think this is a problem. But we're seeing the range in natural background radiation from 1 to 10. You have a dose of 0. We're calculating a number that's so far down here, I only show it with a tiny little red mark, so it's way down below the regulatory limit. But also keep in mind the time perspective. We're sort of trying to extrapolate maybe 1 million years. The rock is 180 million years old and has been stable, for a very long time in its present form, for example, for something like 60 or 80 million years. It was slowly compacted over a very, very long period of time till it was very dense. That's why it has changed slightly, but it's been stable for a very long time. So we think with a system like this we can achieve safety. I just finished by saying what's going on worldwide. Finland, the Finns are very pragmatic people. I don't know if you know them. They're pretty remarkable. They got down to it right away and said, we need a volunteer site. And then they got a volunteer site and in 1999, and they have a construction license application made already, and it's in review, and they'll probably be the first ones to move ahead. And it doesn't mean that they'll be moving instantly, because there are sequential licensing steps. There's a construction license application, and then once it's approved, then they have to have an operating license application, and that'll be 2025 or 2030. But it's a gradual process. Volunteer site also in Sweden, and they made an application in 2011, so this is moving along. In France, they didn't have a volunteer site, but they have quite strong local support for it, and they have an underground lab, and they've made an application to the government, or they will make an application in 2015 formally, and will have pilot operation in 2025. I don't know if you know the situation in Canada. It's quite remarkable. There are 21 communities who volunteered for the high-level waste disposal site, all the way from Ontario to Saskatchewan. They're being evaluated now. First, it's sort of kind of a screening process. Some of them are in crystalline rock from Canadian Shield rock. Some are in the sedimentary rock of southern Ontario, which is a extremely impermeable rock, but it's got the governor of Michigan upset. But that's politics. Anyway, it may take some 10 years to propose a site there, but they are moving ahead, and there are a lot of communities that are engaged in the process. Public acceptance is really a remarkably critical issue. We don't have a volunteer site process in Switzerland. It's an interesting thing, because I think in a sense it was decided that was not really going to work. Switzerland is densely populated, unlike many of the areas in Canada that we're looking at for disposal. Also, Switzerland is rich enough that people don't feel that they need to have something built in their vicinity in order for them to have some jobs or something like that. They have a different perspective than, for example, a community might have in northern Ontario, where the people were miners and things like that. They might have a look at it and say, we can do this. But in Switzerland, they decided and said that it would be based solely on the question of the safest place to put it. Very logical. Swiss are very logical. And we proceed now with narrowing down to try to find sites based on safety first. So finally we think after a long time that we can say that geological disposal is feasible. It's the right way to pursue it. There are many people who will say these magic designs will come along to solve all the waste problem, but as I said, don't believe people who write equations on blackboards. Believe chemical engineers who have to build the plants and keep it clean. You really do need public acceptance. There's no question about that. It'll be a long time yet, I think, before these facilities are operated, probably 15 years before the first one is operated. There's a lot of licensing and approval steps that it goes through, construction, operation, monitoring of a pilot repository first, and all this sort of thing. This is something that's never been done before. Build something to contain wastes for, tens of thousands of years. So naturally, it's a step-by-step, slow process. And the waste, in the meantime, is pretty safe in storage casks. But I'll tell you, my final point about that is that I worry, based on experience with our culture and the way we have handled problems in the past, that long-term storage turns into eventually neglect. That's the type of thing that happens. Or you can have the famous situation like Love Canal is an interesting thing. I always think of it as an interesting case because it was, at the time, built according to the standards for waste disposal trenches. So you can't blame the guys. They were building according to standards. They thought it's the right thing to do. And then the way the site was turned over to the government, who then sort of lost track of it when they turned it over to a school, which was allowed to build its foundation directly through the trench. The worst thing that can happen is just sort of people stopping caring. And if you think that we can sort of store this for hundreds of years, remember that we might not have any reactors. For all I know, we won't have any reactors 50 or 100 years from now. We might not. We might have fusion reactors or whatever. And if the utilities, don't exist to look after this waste, who's going to look after it? So I think you have to start looking after it now. And that's where I end my talk. Thank you for your attention. Thanks.
Before Lawrence runs away, I'd like to open up any